This lesson is on scientific notation. Scientific notation allows us to represent very large or very small numbers in a more concise format. The definition of a number written in scientific notation is that it has this form. It's a number that is less than 10, between 0 and 10, times 10 to the power of some integer. For example, this number here, written in standard notation, would be written as 9.2 times 10 to the 7, because if you multiplied 9.2 by 10 7 times over and over again, it would move the decimal forward 7 places, leaving you with 92 million. Let's look at some examples. These examples are asking us to convert a number in scientific notation into standard notation, which is a regular number. So we can see that 0.15 times 10 to the power of 5 would be 0.15, but then every time you multiply by 10, the decimal place moves over by 1. So if you multiplied by 10, it would be 1.5, move over again, and you move over 5 times, so that the decimal ends there. Now any missing place values will be filled in with zeros. So this actually is the same as 15,000. Now recall that if your exponent is negative, that actually means multiplying by 1/10 6 times over and over again. Every time you multiply by 1/10, you're actually dividing by 10, meaning the decimal is going back 6 places to the left. So let's start with 9.8, and we're going to divide by 10, divide by 10, divide by 10, 6 times over again, leaving you with the place value ending right there. So you can fill the rest in with zeros. So that gives you 0.00000098. So you'll notice that positive exponents result in moving the decimal to the right, negative exponents result in moving the decimal to the left. That's when you're converting from scientific notation out into standard notation. You could also be asked to convert standard notation numbers to scientific notation. So this actually shows you the use of this. If you had this big number here, you wouldn't really want to rewrite that number every time you wanted to use it or represent it. So we're basically just regrouping it into a specific format called scientific notation, and we want the first number to be between 0 and 10. So we can't take 10.5, we can't take 105, we want to take 1.05, and in this case, because it's a big number, we're going to multiply by 10 to the power that is a positive power, because we're going to take 1 and multiply it by 10 to get this big number. So let's think about how many places we would have multiplied 1.05 by to get this number that has been given to us. Well, if you were here, you'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places to the right, meaning it'd be multiplying by 10 to the 11th power. A really small number can be also written in scientific notation, and we want to approximate the first number possible, so that would be 5.025. We want it less than 10. Some approximate it just to one place, and some people approximate to one decimal place. You can choose however you'd like. You could choose to say 5.025, which I think is a little more accurate, or you could just say 5 times 10. to the power of, and now let's take a look at what we would have to do to this number to get it back to this number. So we'd have to move it 1, 2, 3, 4, 5 places to the left, meaning divide by 10 5 times. So you could say either 5.025 times 10 to the negative fifth or 5 times 10 to the negative fifth, depending on your approximation level. For the purposes of our class, you can answer like this on any things you hand in to me. However, the textbook might approximate it a little bit differently. You may also be given numbers in scientific notation that you need to combine. And notice that rather than writing these numbers out, they've left them in scientific notation and they want you to leave it in scientific notation. It actually allows us to calculate almost a little bit more efficiently, so let's check it out. Notice that if you go 3.1 times 10 to the negative third times 5 times 10 to the fifth, it's all multiplication, so it doesn't really matter what order we multiply by in. So take 3.1 and multiply by 5, and what do we get? 3.1 times 5 gives us 15.5. Now if we take 10 to the negative third times 10 to the fifth, remember that when you have numbers of the same base, so powers of the same base, you can add the exponents when you multiply them. So that would be 5 minus 3, giving us 2. Notice that this is 15.5 times 10 to the 2. Almost looks like scientific notation, but it doesn't quite fit the criteria for the format. Remember, this number here needs to be less than 10. So how do we move it one place back? Well, to compensate, you'd want to have the same number, you'd want to have 1.55, but to compensate for moving one place back, you want to have one place forward, extra. So that, let's just check if this would be the same thing. 15.5 times 10 to the 2, move it 2 places to the right, would be 1,550. And this would also be 1,550 if you moved it 3 places to the right. So you can just check on a smaller example to see if you're adding or subtracting in the right direction, but this would be the final answer here, 1.55 times 10 to the third. The second example here, we have a division, so we can proceed in a similar manner. We'll take 8.4 and divide it by 0.2, and we'll take 10 to the 4 divided by 10 to the negative 4. So 8.4 divided by 0.2 gives us 42, and it's still multiplication times 10 to the, and remember, when we're dividing powers, we want to subtract the exponents, giving us 4 minus negative 4, which is 42 times 10 to the 8th power. So this is not quite left in proper scientific notation form yet, so we need to make it a 4.2. So you need to compensate. Because we need to have it go back one, we have to compensate so that it goes forward one extra. Here's another example. They're telling us that 1 light year is this many miles, 5.87 times 10 to the 12. They want us to use scientific notation to express the distance in meters. So it's a conversion of miles to meters, given that every single mile is 1.61 times 10 to the third meters. So now first you need to decide what you're going to do with these two numbers. If every single mile is this many meters, then we want to multiply. So we're taking 5.87 times 10 to the 12 times 1.61 times 10 to the third. And similarly, as before, we can multiply the coefficients, the first numbers, 5.87 times 1.61, giving us 9.4507. And we can also multiply the powers of 10 and we know that that's 12 plus 3, giving us to the power of 15. And in this case, our number here is less than 10. So we can leave it as is. 9.4507 times 10 to the 15 is the number of meters in a light year.